Yes, all right. So, thank everybody for coming. If there is something good we can say about this pandemic situation, is that we are having plenty of funds for inviting people, very good people from all over the world. So now we have Giuseppe Gaeta from the mathematics department of the Milan University. He's an expert in dynamical systems, mathematical physics, and mathematical biology. And since the beginning of this pandemic, he has already written, I think, 3 or 4 papers on COVID-19. One of them I thought really inspiring, so it inspired my own work with Gustavo, which is here. So it's a pleasure to me to introduce Giuseppe. Please start, Giuseppe. Peço a todos que desliguem seus microfones, por favor.
Só um minutinho, eu não estou vendo a apresentação do Giuseppe.
Eu estou vendo.
O que vai? No meu não está.
Professora, a senhora deve ter clicado para alfinetar alguém. Clica...
Vou sair e entrar de novo? Tá vendo?
Não precisa não. Vai no Giuseppe e clica nele que vai aparecer a tela.
Vou no Giuseppe, apresentação. Aqui, consegui.
So,
tá bom?
Tá bom.
Go on, Giuseppe.
Okay, so the first thing I should say, I will not say, but just write, and is this. So, I'm sorry, but you have to cope with English, or if you prefer, I can speak Italian, but I think English is better for you. Now, thanks a lot for inviting me. It would have been much better to be there, but these days it's not possible. When Armando told me, I thought you were interested in COVID since we interacted about this. But later on, I realized that he had already given a talk about this. So I will try to give some kind of transversal talk. And it's a bit difficult to speak without, there is no way to keep my talk and your faces. Huh? Okay, well. And so what I want to do, well, first of all, I should say that it's true that I've been working about COVID, but by now I am a bit fed up with that. So don't expect anything new, especially Armando, with respect to what you already know. Now, of course, these things has attracted the attention of everybody by its brutal way of attracting attention. But the strange thing is that we have a lot of models which basically develop on the basic Kermack-McKendrick model, the SIR, and this is a model from the 20s. It was developed to describe an epidemic of plague in India. And in that case, the epidemic was in I don't remember if 05 or 08, and the papers were in 1920. So they took all their time. But now instead we are trying to do this while the epidemic is still developing. And this makes a huge difference, not only from the practical point of view, but also from the mathematical point of view. So, first of all, I will simple is still so used in these days. And also, what are the problems that we have when we are trying to use the model on something which is developing, not which has been concluded and on which we have all the data, but on which we get new things every day. And then also, I would like to speak about some special features of the COVID with respect to more usual one, and how this can be considered in the models, but actually will not say much because this is, I think Armando already told you about this point of view, and Armando should tell me. And then if there is time, I will tell about other contribution. Otherwise, I will just refer to some papers of mine which are in the archive. Now, I don't like to speak about things I don't know, and the only thing I know is basically the Italian situation. And as you know now, the situation in Italy is much better than a couple of months ago. And say now it would be more interesting to see what happens in other places. But as I told at some point, as soon as the situation got more light here, I was basically fed up with this kind of things. So we had this absolutely unwanted privilege to be the first Western country with COVID, and I will speak about the experience that we got in this situation. And the title was a strange one, so I want to come at several points in the talk to a relevant practical question, namely on the dynamical aspects of the development. Those of you who are familiar with the Kermack-McKendrick model know that now we will see in a moment, but we can say a lot about the trajectory in phase space of the model, but much less about the timing. But usually when we teach courses about this, we are very happy with this. But now that we are ourselves in this situation, instead we would like to know what will be the time development of this, for how long it will go on, for how long it will grow, and so on. So Armando told me that there should also be students and that I should not give for granted the knowledge of the SIR model. So if it is not the case, I can just skip this part. No? Should I? Oh, you have all muted microphones, so nobody can react. Okay.
I think you should say that.
Okay. So, first of all, who are the characters of the model? We describe the situation using three classes of people, which are the susceptible, so those who are healthy so far, who are susceptible to be infected, the infected, which we assume are also immediately infective, otherwise there would be some, I don't remember the English name, say some people who are already infected but not yet infective, but in the simplest case, we assume that those who are infected are immediately infective. And then the R class, usually when you teach, you say these are recovered, but these are more precisely removed. And we will see in a moment that these things, in this case, are different. So removed are those who are not anymore able to infect people, who have been infected and infective, but who are not participating anymore in the infection, in the new infections. Now, we know that these are the characters, and we should say how they evolve. So, if you look at the time t plus something, the susceptible will be the old susceptible, the old susceptible, I have troubles in saying that. So the old S minus the newly infected. The infective at a later time will be the old infective plus the new infected minus those who are not anymore infected, or at least who are not anymore infective, that have been removed from the dynamics. And the removed remain removed, so they are the old one plus the newly removed. Now, already having said these very simple things, we are already saying a lot about our description. First of all, this is what physicists like to call a mean field model. So we only consider average quantities. All individuals are considered to be equivalent. We only consider if they are susceptible, infected, or removed. We don't say you are young, healthy, you are old, easily infected, and so on. So they are equivalent in the health sense, but they are also equivalent in the social sense. We all know that people who live in a small village, removed high in the mountains, have much less contact than people who live in Sao Paulo or Rio. But we consider all people to be completely equivalent. We are giving some kind of average health situation, average social contacts. We are losing all the structure. We we know that this kind of description is completely fails. Old people get ill more easily, healthy people are easily recovered or are more difficult to infect. If you have more contacts or more easily, you get also more easily in contact with the pathogens. So for example, people working in the supermarket, they're in a terrible situation. Personal attitude also makes a big difference. I guess it's the same there, but we have seen in these days that there are people that get completely paranoid about avoiding all possible kind of contacts, people who don't care, and all the graduation in between. And this, of course, makes a difference in the probability to get ill. And as I said, it's the same. It's different to be in a big city or a small hamlet. So we know that people are not equivalent, but we don't care. And we go on. Now, assuming that anyway we want to give this very poor description, what is in the model? I wrote new infected, new removed. So to make really a mathematical model, we should say what is the quantity of new infected and new removed. Now, this depends on how the illness is got. So if you look, for example, at a pulmonary infection which comes from pollution, then it will be completely different. But here we're talking about an infection that comes by contact. I wrote direct contact, but of course direct depends on things and on the kind of pathogen. So in this case, we know that it's direct by coming near enough and breathing what is expiring from the other people. So the new infected, new infection comes out of a contact between an infective and a susceptible. So the number of contacts will be proportional to the number of susceptible, the number of infective, because we say that all people behave in the same way. So the only thing that is left is their number, their fraction in the population. And it will be, of course, proportional to the length of time on which we make these two measurements, before and after. If the length of time is small enough, there will be a direct proportionality. And then there will be this innocent-looking parameter alpha, and everything is in here. It's how easy it is to get infected if you come near enough to an infective, how careful you are if you use masks, gloves, and any other things. So all the medical facts are hidden in this parameter alpha. Now, who is removed? Removed are those who are not anymore infective, are those who are not anymore in this newly infected term. So these are those who are recovered or those who are removed in the sense of being in the hospital or being isolated at home. All these things don't depend on contacts. Removal, so by recovering or removal, is an individual process. So it's not depending on a product, but depends only on the number I. And this, of course, is an even simpler assumption. I say that for any length of time, there is a certain fraction of infective which are removed, either recovered or put in isolation. So this, of course, is not happening like this. We are not electronic parts. But what I mean really is that there is an average time between infection and removal, which is 1/β. And so I put this beta, and you know that when I solve the linearized equation, I will have something like this. Now we have a model, we can work on this. I just rewrote what I wrote before, but instead of newly infected and new removed, I put quantities. And of course, we have a delta t. What we do is that we took these things on the left, we divide by delta t. And of course, then we pass to delta t going to 0, and we get differential equations. So we have a set of 3 differential equations. Actually, we had a set of 2 important differential equation, well, this one is just an integration condition. If we know the solution for S and I, then here we only have to integrate to get R. So we have a very universal model which depends only on two parameters, alpha and beta. And these are already taken to be real, of course, and positive, so the signs appear explicitly here. Now, if you look at this equation, you see that the number of susceptible is always decreasing. I make that there are no newborn, no deaths. If that's because of the illness, they are surely removed, but there are not people dying for other things. Basically, this works if we work on a short time scale. If you want to describe things over several years, then newborn babies are relevant, but if you want to describe things over some months, it's okay like this. So S is always decreasing, while the number of infected can be increasing or decreasing depending on who wins among these two. So I write gamma is beta over alpha, and the number of new infected, the rate di in dt is these things, and I forgot, here there should be an I forgot to write this, but I is always positive or 0, beta is always positive. The only thing that can change sign is this st over gamma minus 1. So if S is greater than gamma, this ratio of the two basic parameters, the number of infective is increasing. If it is lower, then it is decreasing. So gamma is an epidemic threshold. And we also know that the maximum of I will be reached when S is exactly equal to gamma. Now we can also say what will be the maximum of I. We put together the equation for I and S, and this is a simple separable equation. This is the solution. Oops, sorry. So this is the maximum we get when S is equal to gamma, but in practice, I naught, the initial condition, is negligible, and in this case, unfortunately, all the population is susceptible, so S naught is basically the whole population, and this is the maximum that we will obtain. So this simple model gives us a precise prediction for what will be the epidemic peak, but it does not tell us when it will be reached. And of course, this prediction is completely unuseful in the sense that this would happen if alpha and beta and so gamma were constant. But when things begin to go badly, of course, we try to do a lot of things to stop the epidemic. So this works if you have an epidemic of cold, nobody cares about this, the parameters remain the same, and you can predict what happens, but not for a serious epidemic. Anyway, the important message of this simple model is that the epidemic peak depends only on this ratio beta over alpha, not on the individual values of alpha and beta. And to lower the epidemic peak, we can either raise beta, which means that we would remove the infective, have them being infective for a shorter time, or lower alpha. Lowering alpha is what in these days is called social distancing. And I don't know why we speak of social distance, because what we really mean is physical distance, reducing contacts. You are free to see your friends on the internet. Actually, it would be perfectly safe to see your friends at some distance, at 2 meters. There is no need to be locked inside the house, except that if you live in a big city, of course, if everybody is around, then there is no way to keep distances. But if you live in a small hamlet, there would be seriously no problem. Other important things is that this model gives no information about the timing. Actually, it's very strange because we've been teaching these things for years and years, And there was nobody really taking care of giving an exact solution of the model. We can get easily an exact solution in some approximation, but not a complete one. And in this year, a lot of papers were published with a complete solution. It's just a change of the unit of time, and then you can solve this. Okay. Now, we also hear often in the media, at least in Europe it's like this, but I guess in Brazil it's the same, this mythical parameter R0. So the basic reproduction number. In between infection and removal, each infected individual transmits on the average the contagion to R0 susceptibles. R0 is this alpha. Remember, the number of new infected in time delta t was alpha times S times I times delta t. But if you look at the number of people infected by single infective, so I is equal to 1, we get these things, but delta t was 1 over beta, so we get alpha over beta times S, which is just S over gamma. And I repeat, I don't know what happens in Brazil, but in Europe, all the politicians, especially after this famous speech by Merkel, focus on this parameter R0. If this is lower than 1, the epidemic is going down. If it's higher than 1, it is developing. Now, sorry, what happens? Okay. Now, in the initial phase, S is basically the whole population. S0 should be N, the whole population, and this is the basic reproduction number. So this is the simplest measure of how quickly the epidemic is spreading. In my opinion, this is too simple and does not describe much, but it's a fact that public opinion wants to know about this. So these are the numbers for a few known illness. So for the standard influenza, we have 1.5. For the Spanish, 1 century ago, it was, for what we can reconstruct about the data, it was about 2.2. Pertussis is 5.5. Measles is very bad, is 15. Smallpox is 5. Rubella is 6. Mumps is 5.5. And we were told in the beginning that COVID was 3. What means we were told in the beginning? In the beginning, we had data from China, and we could fit the data to have this number. And of course, we know very well all the other illnesses that I listed before, but COVID is very new, so we should have some doubt. On the other hand, we could be relieved that if it was as lethal as it is COVID and as spreading fast as measles with 15, then we would be in even bigger troubles. But the problem is that we had 1 century or at least of data on all the other things, and we have a few months for COVID. So are we sure it is really like that? The answer is no, we are not that sure. And I think that the answer is also no, it is not like that. But we will come back to this a bit later. Now, as I said, we have this simple model. And if you look at the papers, in particular from the British groups that were fighting about lockdown or not lockdown, and all the discussion was based basically on this kind of simple models, maybe a bit less simple than 3 classes only, but this kind of models. So I would like to speak 10 minutes about this. Now, the problem is that, as I said, we know that these models are fails in the sense the situation is much more complex. We have structure by age, we have a geographical structure, we have a social structure with some kind of people meeting a lot of other individuals and some people living pretty much isolated, having less contacts, less occasion to get infected. But the problem is that in this model, we have just these two parameters, but we should know what are their values. And we should know that immediately, because it is in the beginning that action is effective. And this is completely different than what we are used to teach or to read in the book. Questions, epidemics of 1 century ago, or measles, we have data over years and years and years in a lot of places. Now, what happens in the beginning? In the beginning, you know that everything will be exponential. Not everything in mathematical sense, because we can build strange examples, but anything applied in physical or biological sense, there will be a linearization which is non-singular, and everything will be exponential. So I believe there are some students, I cannot see who is looking at me. The example I'm used to use with students is the replication of bacteria. The mass of a bacterium is about 1 picogram. The replication time is about 20 minutes. And this is the conversion to days. The Earth has a mass of 6 times 10 to the 24 kilograms. And suppose we have 1 bacterium and it starts replicating, and it is not limited by the scarcity of resources. How long it would take for the lineage of a single bacterium to reach a mass equal to that of the Earth? I will not give you the solution. I'm sure that when you make the computation, you will repeat it several times because the answer seems impossible. And okay, this is what we should do. The non-student know, and I hope also the student know how to integrate an exponential. Now, in the case of coronavirus, what we had in Italy, the initial cluster was in a small hamlet near Piacenza called Codogno, and on the 20th of February, we knew about 6 patients. Later on, we realized that the virus was around since a couple of months, actually. Maybe I should tell something about that later on. And the initial phase, the doubling time of, well, okay, there is some mixture between English and Italian here, was about 2 days. The Italian population is 60 millions. And going on with the initial doubling rate, the whole of Italy would have been infected in 48 days, end of March. So this is a stupid computation, but in Italy, and I believe also in Brazil, and I believe also in a lot of other countries, one of the problems in the initial phase was to let the politicians understand what is the effect of an exponential growth, how fast things can go, and what happens by waiting 1 week more or 2 days more. And so if you look, for example, at my paper, you see that the initial things was really written with the idea that this is read also by people who should read it, but who don't really know what is going on. Then the published version is a bit, I hope, is a bit better from the mathematical point of view. Okay, so the cases grow very fast in the initial phase. What about the data? Now, typically health authorities give daily data, and it will make no sense to give more frequently data. I mean, even daily data, at least in Italy, it was a kind of, well, if it was not tragical, it was funny in the sense that there was clearly a weekly fluctuation due to the fact that people were not able to transmit the data in the same rate every day. And in this case, not because Saturday and Sunday was to rest, but because the hospitals were overwhelmed and so on. So basically, we get 1 more data each day, and we cannot really put together data from different sources. The situation in Italy is completely different than in Sweden, is completely different than in England, is completely different than in Brazil, and so on. Within Italy, the situation was completely different from one city to the other. In Bergamo was something, and in Palermo there was basically nothing. And I'm sure in Brazil it's also the same. So you cannot really build big database. And this is a problem because in a SIR type model, you have to estimate two parameters or a bit more if you have a more refined model. Say 2, 5, maybe 10 parameters. So after 1 month, you have some statistics. There is still the old saying by von Neumann that with 4 parameters you can fit anything, but anyway, it makes sense. You have 2 parameters to fit, you have 30, 50, 60 data, you can get something. But if you try to make a network model, there are two cases. Either you already know what is the network, what are the contacts between different cities, for example, or you have to infer the data from these connections from the data. Now, of course, we have years and years of data about flu, but the problem is that they are useless in this case because really, unless you are old and you have serious health problems, you don't really care much about the flu. If you get the flu, you stay 1 week home, and okay. But in this case, it's completely different. So if you have a flu, there is no lockdown for the flu, there are not use of masks and so on. So the network in this case is completely different. So for example, in Italy, there was some paper building a wonderful model with the contacts between provincia, so departments, or even at a smaller scale. The problem is that the contact metrics, and when I speak of metrics, I'm saying a lot. I'm saying that we are considering linear expression for this, is a 10 to the 4 elements matrix. But after 1 month, you have 10 to the 3 data. And so you should wait a lot of months to have one data for each elements. I don't speak about making averages or standard deviation. And basically, this is why there is no sense in trying to make a network model unless you know how the network is done. For example, I've seen some paper by Indians and working on a city scale and looking at what would be the situation in the slums. Okay, there they have an information about the physical structure of the network. And these are completely different things. But if you have to infer the network from the data, there is no way you can do that in a short time. And by the way, in my opinion, maybe I am prevented, but all the works trying to have information about COVID from artificial intelligence things make little sense. Artificial intelligence works is very good if you work on big databases. But here we have no base, no data. We have data for 1 month, 2 months, 3 months for Italy, and a bit more for China, except that we don't know if data from China are reliable. And so there is no database. There's no way to work just with statistics. You need to have some idea what is going on, and then you can do something with simple model simply because you don't have enough data to work on more refined models. Sorry, I need to drink a bit. Okay, let's go back to our SIR friend. Now, we have seen that in the, sorry, I should say SIR. I say SIR, I'm sure that for Brazilian is not a problem. We have seen that we can raise beta or lower alpha, and this has the same effect on the epidemic peak. But this could, sorry, what is this? I have the impression, no, this, sorry. Something, okay. Okay, sorry, I went one page down and and I could not recognize the line of the talk. So we've seen that the height of the peak depends only on the ratio, beta over alpha. And we were noticing that there was nothing about the time needed to get there. But we can look back at the equation. So these were the equation. Now, if I multiply alpha and beta by the same factor, the right-hand sides are multiplied by this factor lambda, and to multiply also the left-hand side by lambda, I should multiply t by lambda to the minus 1. So the equations are invariant under this transformation, which is a simple scaling in the parameters and in t. But you know that if I make this scaling in the parameter, the ratio beta over alpha remains absolutely the same. Lambda above, lambda below. But the time is changing. And now this is what happens. In the solid curve, I've taken some reference value for alpha naught and beta naught. Then for this curve, I have lowered alpha and lowered beta. And you know, I arrive at exactly the same number of infective at the maximum, but instead of getting there in 40, whatever the time unit, I get there in 80, more or less. And if instead I multiply alpha by 2 and multiply beta by 2, I get this curve, I get there in half of the time. Of course, you say, who cares? What I want is not to act by raising and lowering both. I want to raise beta or lower alpha or the two. Now, of course, we should try to do both of these things. Raise beta, get people isolated more quickly, or lower alpha, get less contacts. The problem is that both of these actions have a big cost, whatever you mean by cost. To raise beta, it means that you should be able to isolate people more promptly. So you should be able to perform tests more quickly. You should have a lot of places in the hospital or a lot of places where to put people to be isolated. To lower alpha means basically lockdown, which means a huge economical cost. So suppose that in the best of possible world, you should do everything to lower the rate of expansion, but you're not able to afford both of these actions at the same time. Now, what I do here is different things. This is the reference curve, the solid one, and on the dashed curve, this one, I act only on alpha, so I act only on the social distancing. I basically nearly half the epidemic peak, but everything goes on much slower. While if I work on beta, I arrive at the same result. I know that is exactly the same result because the gamma will be the same as for this other curve, but it's a bit slower, but just a little bit. So basically working on beta, I can reduce the peak without slowing down the epidemic. Now, the fact that I don't slow down the epidemic can be an advantage or a disadvantage. If I am in the situation where the hospitals cannot cope with incoming patients, then it's definitely better to slow down things. So I get less people coming each day. I will have trouble for a longer time, but I have more hope to cope with the situation. But if I am in the situation where already I manage to give care to all the people who are infected, and then I should try to keep the problem of lockdown for a shorter time, and in this case the accent should be on the beta. And this is what happens if I do both lowering alpha and increasing beta, and of course I get a much better situation if I am able to do this. And okay, these are the things, and this is a type. Okay, a safe level is when you arrive to some fraction of the population infected. I don't remember if it is 10 to the minus 5 or something like this. And this is when you start getting in troubles, and this is the time for which you should keep the lockdown, and this is the time in days. Yeah? So in the beginning we were not publishing this data because it was a bit too pessimistic, but by now things went worse than we could imagine. So, okay, so this was to say that if you work with a standard SIR model, there is this big difference in the timing depending on which parameter you want to act on. But we would like to consider a more refined version of the model. So more refined version, which have been considered in particular, are classes where you have model where you have more classes. For example, people having the illness in incubation, or people separating the situation of being in the hospital or being at home, or different degree of infectiveness, and so on. Or people with this is the simplest case where you keep just the incubation, this expecting class, or multi-compartment model, for example, people between 0 and 20, or 20 and 40, 40, 60, 60 on, or different regions, and so on. Now, of course, there is no limit to the complication you can introduce, and as usual, the more refined, the more detailed is the model, the more you hope to get a precise description of what is going on. The problem is that the more complicated is the model, the more refined is the model, the more complicated it is, less information you're able to extract from this, and moreover, less data you have to fit the information. So the problem is what kind of phenomena you want to describe, or if the phenomena is the spreading of the COVID in the general population, is which aspects of the phenomenon you want to focus on. Now, what happened in Italy is that we had, when it arrived, we had only the experience from China and something in Korea, but Korea, Taiwan, especially Taiwan, were very effective in stopping the epidemic, so good for them. They gave good suggestion on what could be done. We were not able to do that, and but this means they had the few data. So in the experience from the China report, the joint report in particular, I'm thinking from the Chinese Disease Center and the World Health Organization, there were two things which were relevant. So they were not in this report, two things that were relevant and which we in Italy were faced with, and they were discovered. By the way, they were discovered in a strange way, I will say in a moment. The first fact is that a large part of the infective is asymptomatic. With our model, the estimation of this large part means 90%. It's not clear what asymptomatic means. Maybe you have very mild symptoms. If you sneeze a few times per day, you don't think that you are ill, just that, okay, there is something. So this is not clear if it is completely asymptomatic or asymptomatic, but a very big part. And this was discovered in this work by Crisanti and others. They were lucky in the sense that one focus was Codogno, but the other was a very small hamlet. Very small means 3,000 inhabitants. The place was completely closed, and they had this idea of testing everybody and testing everybody several times. And so they realized of this fact that there was a big percentage of infectives that were completely asymptomatic. And the other things which was discovered is that we thought in the beginning that people infected with COVID would die of pneumonia, but then making autopsy, it was discovered that actually in most cases, what happens is that there is a pulmonary microembolism. And for a mathematician, this is absolutely the same. But for a medical doctor, it makes a big difference because they know how to treat embolism. There are standard medicaments like heparin, which can be used for this. And this is one of the reasons why in Italy there was a big drop in the mortality rate. This was the good reason. The bad reason is that in the beginning in Italy, like in many other European countries, the infection got eradicated in senior people residences, and there was a very high mortality rate there. And this, of course, is not reproduced in the sense that you have already killed most of the people that could be killed in this way. Now, the strange things about the way in which these things were discovered is that both of these facts were discovered by going against the instruction from the health ministry and of the World Health Organization. The health ministry said that tests should be done only to people with symptoms, and we discovered this fact of the asymptomatics because some universities decided to test everybody. There was also some, okay, I don't want to enter into the story of this. And the other instruction was not to perform autopsy on people dying with COVID, both because of the danger of doing this, of spreading the infection to doctors, and because it was clear they were dying of COVID, that there was no time to be wasted. So this old Italian habits of not respecting authority in this case, at least for this side, was positive. Now, okay, time is going fast. How long are your talks usually? I mean, I don't know if it is half an hour, 45 minutes, 1 hour. Of course, you cannot answer. They are muted, so you can make
No,
with.
I will answer. It's okay. 1 hour is okay.
Okay, I hope to be shorter than 1 hour. And okay, now one of these slightly more refined model is what we call SIR, and A is because of asymptomatic. I repeat, this does not want to be a good model. This want to be a brutal model, very rough. Just with respect to the standard model, it introduced the fact that there are asymptomatic carriers. On the other hand, I know that everybody knows that Armando has been working on these things. Actually, they consider that Armando and Gustavo, I think, I don't remember the name, Gustavo, yes, they developed this, and surely they have talked about this model. So I don't want to enter into details, also because I see the watch and I've been a bit too slow on this. So these are the equations, and S are always the susceptible, I are the non-infected, and J are the asymptomatic infected. So you see, upon infection, a healthy individual gets either to this with the probability Xc or asymptomatic with the probabilities 1 minus Xc. And the rate of removal in the case of symptomatic is beta, is the time before being recognized as infected and being hospitalized or isolated at home, while in the case of asymptomatic, well, there we have to wait, he recovers naturally. So these are wildly different parameters. The time to hospitalization is about 1 week, is 5 days to display symptoms, and okay, you don't go to the hospital to the first cough or sneeze, and it takes, once you get to this stage, it takes about 2 weeks to heal naturally. So this is 1/7, this is about 1/21. And we fit with this, the model goes quite well. As for the SIR model, the relevant equations are the first 3. The way to solve exactly the standard SIR model does not extend to this one. So that is why I didn't want to to speak about these things. And what happens to the basic reproduction number in this case? Well, I can rewrite the equation by saying K is the total number of infectives, and now B is the average removal rate. So if X is the fraction of symptomatic over the total infectives, I should weight beta with a weight X and eta with a weight 1 minus X. If I do this, I have this reproduction number, not alpha over beta, but alpha over B. And this, since B is lower than beta, this is bigger than the R naught I would consider just from the symptomatic. And here is the problem. When we gave this value of 3 for the reproduction number, this was taken from the Chinese data, which didn't consider the asymptomatic. So what happens if we consider these things? Of course, we should see what is alpha, what is beta. There is the problem that this parameter x, this fraction, is not constant, is changing because the asymptomatics stay in the game longer. Anyway, in the beginning, it's basically the fraction x is equal to the probability of being symptomatic, and if we put this value inside, what happens is that the real R naught is a fraction of 5 over 2 of the R naught that you have measured from the symptomatic only. This was 3, so this is 15 over 2. It's 7.5. It's not measles, but it's much bigger than we would imagine. And so there was a good reason why a lot of countries thought that they could wait. A lot of European countries, especially in the north, they thought they could wait for lockdown and not to keep it too long, to wait. The situation was getting serious enough, but things were going much faster than we could imagine from the data of the symptomatic alone. So this was in part because, as we scientists always say, that the politicians don't know what happens, but also it was because the model was not taking care of a very important fact, that a lot of asymptomatics are around. And especially young people are asymptomatics, but young people are also more active socially. So this estimate 5 over 2 could be bigger if you really consider the structure of the population. Okay, now what we did was to integrate this equation, this model for Italy, just to have an idea of if we can work on this model or not. And this the problem is that we had these governmental measures reducing the social contact, and so we had to fit. Of course, things were not in step, because people also get scared, or at some point get tired of being scared, and there is a continuous changes. But we worked with a step-like function and with these parameters, and this is what happens up to mid of June, and you see the fit is qualitatively very good. Then if we start discussing with the statistician, then we could see. But remember that there are only 2 parameters in this, no, 4 parameters, because there are also eta and xi. Eta and beta actually were estimated from the medical considerations, so only alpha and xi were fitted, and there was this R, this reduction factor, which is changed over time, and this was fitted. Now, I should also say that there is a mystery in this. So this is one, okay, this is the reference things. This is the first step of restrictive measures from the government. This is a second one when we really got locked in. But this is around 25th of April. There is a delay of 2 weeks, so this is around Easter. Now, there was nothing on Easter. What happened on Easter is that after Easter, the law did not change, but the attitude of police changed. We get more relaxed, so we didn't get locked in, but the contact rate seems to have diminished. Another things that happened is that summer was coming in, so maybe there was more ultraviolet, or maybe just the fact that individual protection devices, which were not available, not even for the hospital workers, at some point began to be available. So we don't know what happened. Anyway, things changed a lot, and this is the situation. This is the cumulative number of cases. And so you see this is getting flatter and flatter. Now, what I wanted to focus on in the beginning, I said, was this fact that we could have been, in the SIR, we could have been raising beta on lowering alpha, same effect on the peak, but a different time development. And the same things happens here. What happens? Sorry, I have a problem. Okay, sorry, I pass. I don't have a problem. I had the problem in the sense I was not in time to finish preparing things. So I'm using a picture from a paper, and here is the same things that happens in this model, except that here there is a problem. Namely, we don't really care about the number of infected people. We care about the number of infected people with serious health condition. So we had to make some consideration about this. And as usual, the solid black curve is the reference one. This dotted one is obtained by acting only on the social distancing. There is not much effect. Sorry. No. The blue one is with the social distancing, so there is an effect, but there is also a slowing down. And this instead is acting on the beta. So there is no slowing down, but the peak is lowered a lot. And this is combining other things. But the message is that even with these things, taking into account the role of asymptomatic, the same things happens. Namely, if you only work on social distancing, then you lower a bit the peak, but you slow down the things a lot. This is the social distancing in this case. If you work on the beta, you lower the peak. And in this model, you can also work on a different things, namely on the Xi. The Xi is the fraction of people who get infected and are known to be infected. So in the natural situation, being known to be infected means having symptoms. But if you test also people who are asymptomatic, who don't display symptoms, then you can increase the fraction of people who are infected and who are known to be infective, and so who are isolated with the time beta to the -1, not with the time eta to the -1. So, and this is why you get these different colors with different mixture of these things. And the result of this simulation is that what really matters is not increasing Xi by having random tests, but increasing beta. So isolating as quickly as possible all the people that you know to be infected. The problem is that this is complicated. You must trace the contacts of known infectives. Of course, this raises privacy questions, but this was big debate in Italy, but in the end, it turned out to be completely useless because the app was not downloaded by people and it didn't produce any tracking. The tracking is made by hand, which means people in the hospital, humans, speak to infected people and reconstruct their contacts. And this is done by people who have some medical training, so who know what kind of contacts are more at risk and which one are less at risk, and so on. So, okay, the other things I would have liked to say, but I said if time permits, was to speak about other SIR type models, but this is just this final page in this paper, which is in the archive. So I will give you just this reference. I just wanted to end up on a positive note. So I would like to speak about two papers which give some hope. One is a very recent paper by a group from Rome, and they find some correlation with the blood type. So in the sense that people with some blood type are more easily infected. So this gives us some hope to understand more. I have no idea how, but it gives to the doctors some new idea, something which was indeed extracted by statistics. So I am a bit going against what I said before. So this is group by Rocco in Rome, and the other is this 50 is a paper by Britton, not Nick Britton, the one of the book, but this Tom Britton. And they observed that indeed there are people who have more contacts, so they are prone to share, to spread the disease more easily. For example, people working in the supermarkets or in the transport or so on. But they're also more easily infected. So they are probably, the fraction of them who already got the COVID is higher than the fraction in the total population. And this means that to reach this herd immunity, probably it's enough that in this class of people with a lot of contacts, there is an high rate of people being infected. And so the herd immunity level in the total population is probably lower than what it was expected. Okay, I see that my time of the hour is definitely over, and I seem it's time to stop. I realize only now that I'm not from the last part.
I thank very much
Only
Giuseppe for
probably I didn't share all I had to share. Okay.
So I thank very much Giuseppe for this beautiful presentation, and ask you who wants to ask some questions. Questions, please don't be shy.
Giuseppe, what are those data you didn't want to show?
Let me see if I can manage to.
Is that social distance for 6 months? Is that?
These things you have not seen before, right?
Yeah.
Okay, so this was the fit of the Italian situation with the model, and this is, sorry, I have to find it again.
You have a table with a time of lockdown, I think.
Yes. It seems I cannot show more than one page. I will manage. I will stop and then show the whole, my entire screen. Okay. Okay, so what are we talking about? This table? This one?
I don't see. No. Yes.
No?
Yes. Yes.
So these are the things
Yes.
that I was showing. These are the things that I thought I was showing, but I think you have not seen it.
6 months of lockdown?
Sorry? 6 months of lockdown. Yes. Yes. That's why we got very scared and
Okay. And more. 226 days.
126 is more than 6 months. Yes.
Yes. It's almost a year. Okay.
Yes. So basically, this means that if you are taken by surprise, you should make the lockdown because this is the cheap way, it's the easy way. But it's not enough to do that. You should organize something and try to follow the contacts of
Yes.
things. It's costly, but and it requires organization. And I must say that basically in Italy it was not done. It was done in some region. In Veneto, it worked very well. In the other regions, basically we waited for things to calm down, and now it calmed down. But we don't know if it was the Pope praying on Easter, if it was the sun, if it was using the masks.
So, have you seen the data of Vietnam?
The data of?
Vietnam.
No.
They
No, in
claim they have 0 deaths. Nobody died, they claim.
Yes. It could be they are very good. Or it could be that, for example, we had a long debate because there was a much lower mortality rate in Germany than in Italy.
Yeah.
But on the other side, there was a different policy. In Germany, there were people were considered to be, they were put in the statistics if they were dying because of the COVID. While in Italy, it was if they were dying with the COVID. So if you have a 96 old people with 2 cancers, he gets the COVID and dies. It's not clear. I mean,
yeah.
Actually, sorry.
France must be dead too.
Well, the problem at some point also countries started to change this policy. For example, in Spain, there is a jump because they changed the policy because in the beginning it was a medical question. Then it became a political question because they realized that this data have a political effect and then you cannot trust the data anymore, basically. So, and even the data about the death is not so reliable. I mean, people dying because of COVID, of course, there is this problem, but even the total number of death is not so clear. For example, in Rome, there were much less dead than in the previous year in the same period. And the reason is quite clear, because there was not a big impact of infection, but there was the lockdown, and we have thousands of people dying of motorcycle accidents, and this could not go around in the street. On the other hand, a lot of people were dying of cancer because all the treatment of cancer were stopped because you could not safely go to the hospital. People having heart attacks, you go to the hospital, left very bad, and complicate things. It's not easy
Yes.
to get that. It's much easier to get the data about the Spanish flu 100 years ago because the governments were not concerned about public opinion at the time, so they were not cheating the data. Now we don't know what is going on.
Yeah.
Other questions?
I have. Can you hear me?
I
Yes.
hear the
Go on,
but I
Josh.
cannot.
There's a noise. So, professor Armando and Giuseppe, I have one curiosity. I have asked my apologies because I was late. So I had it's there. I mean,
I cannot hear, but if somebody has heard, they can repeat the question.
there's a feedback coming to me. I don't know what it is. Anyway, I don't know. When I speak, there's a feedback coming. There's someone with the. I don't know. It's a. Anyway, I'll try to make it clear. There's a feedback come back to me. Try to.
Can you write down your question in the chat?
So I try to make it anyway. I point it, first of all,
Okay. It's okay. It was my.
It was your computer.
To turn off the camera.
Okay, now it's cool. Now
No. It was the jack of my headset.
And it
No.
was coming back to me. It was like difficult to. Anyway, my question is a little bit more to Professor Armando because I talked to him by mail. But Giuseppe, feel free to as well to jump in and to add something. Professor Armando, I talked to you by mail, and as I told, there's a friend of mine working with COVID, and he's trying to model how the opinion of people can influence the process of quarantine. So I believe that you said something to me that you saw a kind of talk about that. So you did take into account this kind of opinion spread in your model, no? Don't think so. Did you?
No, not in my model. Well, the model is just like the one presented by Giuseppe. I see there's nothing about opinion. I think it will be a very different kind of model. Very interesting too, but this is not what I did, and I think it's not also what Giuseppe did.
But you try, just a curiosity, I mean, I ask apologies again because I had a problem before, so I could not attend the event in the right time. So I had that kind of problem before. Anyway, you try to use the Brazilian data set. I mean, it's not reliable, but you try to use, no, I don't know.
In my paper, we used the data on São Paulo state, only São Paulo, because they were more abundant at the beginning. But after that, I did not take any other data into account. Maybe I'm going to think about starting some research on data from Belo Horizonte, but I'm not sure about that yet.
Okay, but Giuseppe, just a curiosity. I mean, I ask apologies if I take too much of your time. You said in Italy you have faced problems with the government. They are trying to mask the data, the public data. You said that's not reliable anymore. What it's happening in Italy as well. In Brazil, had this problem. The government doesn't want to show the data to the public.
Well, I think that in a way, Italy was a positive case because we were taken as the first by surprise. So by the time they reacted, it was later in the development of the epidemic. But yes, I think this is unavoidable anywhere. Of course, there is a big difference between China and Italy, say. I completely distrust the data from China, and I substantially trust the data from Italy. But I mean, it's of course at some point the regions were fiddling with the data because there was a completely different situation in different regions, and so at some point nobody was dying anymore in Lombardy, and then all of a sudden they had to put out the data and so on. But I think in general we should just keep in mind that the data have some political impact, and so we should be careful in analyzing this data and trying to extract from the data the relevant information. I think that the more democratic is the country, the more you can trust the data, but does not mean that in a democratic country the data are completely reliable.
Okay, thanks a lot. I should ask apology because I called you by Giuseppe. In Italy, you do not call the people by the first name, but in Brazil, do that. So sorry. I mean, it's not a lack of respect.
No, but I mean, I'm sure they have been not lying, but you know the things of Churchill, that you should lie with no shame, but if when the lies are not enough, then you should give statistics. And this is the thing. You can present real data in different ways. I would say that in Italy it was difficult to understand how much of the mess was done by the government and how much was given by the press or by the media, who like to change point of view each day and so on. But I would say that at least for the first period, if you were going to the sources, the data were reliable. But if you were looking at the way they were presented in the media, they had very little sense, and they had more to do with what the government was trying to transmit. I don't want to say anything about Brazil.
I think that's all.
I'm free to say bad things about Italy, but not about other countries.
Well, we may say those things by ourselves.
We have self-criticism, I believe.
Well, does anybody else want to ask a question? Well, maybe I want to ask one myself.
Okay, let me add one thing to Jorge, that the reason why I stopped was in part because I was fed up with this, but also in the beginning, okay, I know that the paper we are writing were going on the desk of the government office working about this. I don't say they were believing this, but they were reading the papers. At some point, it was clear that they were not only not listening to us, but were not listening to scientists in general, but they were out of the more scaring period, and they were deciding, looking at elections and not looking at the data. So at that point, it made not much sense to continue working on the models for Italy. I don't know if this answers to your question.
So we have the same problem in Italy, because I remember that at the end, that's no problem. The new prime also not listen to the models. He's not listening to science and just taking decision randomly. I don't know. You said that. I don't know if it understood properly. You said that the current government is not to respect science, like in Brazil. In Brazil, have a president that does not believe in science, so he does not take into account model. He does not take into account the research. But you said, I don't know. You said that in Italy you have the same problem now as well. I don't know if
No, I would not say that there is a situation where politicians don't believe science. I would say that the situation now is much more relaxed in Italy, and they, in the weighing the risk, the sanitary risk, the health risk, and the election risk. Now the election risk is more relevant. Okay, but on the other hand, if there are 200 cases in Italy over a population of 60 million, I mean 200 new cases in one day, okay, of course the impact is low enough, and probably it is true that I mean, you can eradicate the virus in one country, but until the United States don't do anything to eradicate it, it's clear that we have to look for living with the virus like we live with the virus of influenza. And okay, in the beginning it was a big mess, and now we don't really care. I mean, at least those who are not too old, we don't really care about influenza. So the problem is to, I mean, there are different points of view, and it's not clear that there is not only the health problem. I mean, you can die of COVID, you can die of hunger because you're out of job. And in Italy, we had about 30,000 deaths of COVID, but usually in 6 months, you have 300,000 deaths of heart attack and similar things. And of course, if you stay locked in at home, this increases the fraction of these things. So even from the health point of view, there is it is not clear what to do. It's clear that trying to track the contacts is important, but the threat is not just on one side. And then when you have different points of view, of course, getting the right balance between things is not easy. If you just say, I don't believe to science, it's just a stupid things. But if you take into account different aspects of the problem, it can make sense.
But unfortunately, Brazil,
I mean,
don't believe in science. The president does believe in science.
I leave the Brazilian discussion to you. I don't want to
Okay.
to say anything. You have seen that I was sort of having some reaction on the Italian things, which was stupid because I think that Brazilian people are free to say whatever they want about Italy, contrary to people from North America. But anyway, there is always some instinctive reaction. So I don't want to say anything about Brazil.
Okay. Okay. Thanks a lot. Thanks a lot.
Any further questions? Well, let me make one question myself. I saw many papers on results of serological tests of random samples of population for antibodies for COVID-19.
Yeah.
I saw in Spain and even in Brazil, we have a large paper on that, a large research. But I haven't seen any in Italy. Do you know anything about it?
In principle, there had to be a large-scale test. And okay, what happened is that they didn't get enough people, and it is possible that the chemical reactant needed for this test will get out of date before they can manage to perform the test. You can wonder why at this point they don't force, for example, military people or police people to take the test, so at least you have one test. But they reached about 1/3 on what had to be the size of the test.
There are also interesting research from our university with people who are searching for the virus in wastewaters. And they published...
Yes, this was also in Italy and in France, of course. This was started in France. There was some panic out of this because the public didn't understand that getting the virus does not mean getting parts of the virus sequence does not mean that there is active virus in the water. But this was done. There was some plan to use this to see in which areas there were this focus of virus. But the truth is that by now the numbers are so small. The only thing is to follow case by case. And of course the numbers are small. But for example, a couple of weeks ago, there were a number of cases in these delivery companies. And of course that is small, but can be immediately very dangerous because if people get to the house of everybody, getting in contact, and so on. So now the situation is more on this case-by-case chasing with attention in case there are explosions.
Okay, any further questions? So let us thank Giuseppe again. It's more than 11 p.m. in Italy.
For me, yes. I hope that it was not too boring. For me, it was boring to speak in front of a screen and seeing just my slides and not being able to look at you. So I don't know how it was for you.
But,
Probably, I think if I will make another talk on this situation, I will try to make a half an hour talk, not 1 hour.
Well, thank you and have a good night. Buonanotte.
Buonanotte.
Grazie.
Grazie mille.
Good afternoon.
When we could travel again,
Yes.
we will meet somewhere.
Yes. But I'm afraid we will have to meet other times in this way. Maybe we will get more used to this and things will be more smooth.
I hope.
Okay, anyway, now I give my talk and finally I can drink, I can have some drink. I was afraid of drinking after dinner, but before the talk. But now before going to sleep, I can have a drink.
I'll drink a good national wine.
Unfortunately, I have only very bad one, but I have some good national liquor. So
Yeah. Well,
So, hope to see you soon.
yes, hope so. Thank you.
Thank you.
Bye.
Bye.
thank you.
Bye-bye.
Good
Bye-bye.
afternoon.
Good afternoon. See you.
Ok. Tchau a todos.